All right, so now that we have I think saturated in terms of people who will be joining this session, let's start the meeting. So today, I want to first talk about what this class is all about. Again, right? This will be a recap now that you got sick of seg files, got sick of assembly, got sick of cache, and probably sick of virtual memory by now. I want to make sure a recap like, hey, I know you're sick of it, but these things can be useful. What you're learning so far is first of all, right? Uh, the first topic that we learn is how to use Linux. Why is that good? Because when you need to develop something from the get-go, if you go to a state-of-the-art research lab, for example, if you go join like a Google Brain team, like they don't call it Google Research because right now Google has a bunch of like research team, things like Google AI, Google Brain, they all do research on different things, right? Um, Facebook Research, Intel Labs, NVIDIA Research, all these places use Unix. Basically, you'll be working in Ubuntu, working in CentOS, like any Linux-based operating systems. So hopefully that first part of the lecture kind of give you a good overview of like, okay, this is what you're going to see. If you start to do frontier, like really frontier research, uh, not even research, actually, like when you do a frontier like product development in a company, they will use a lot of Unix and Linux. Then we cover C. Why do we need to learn C, right? It's one of the languages that sit really close to hardware. The fact that you can control the memory address, that allows you to do a lot of things involving how you manage the cache and how you manage the virtual memory in some sense, right? If you look at the kernel code, if you somehow go crazy and download Linux distribution and actually look at their implementation, you see that that's also done in C++. C++ is like a fusion of C and Java, object-oriented like programming styles, right? The syntax looks like C. Then you bring in object-oriented programming. So if you're curious about like, okay, what's next? One of the things I definitely recommend is that look into C++. You will notice that a lot of things are basically similar to C, but you have objects, so it's a little bit easier to program. It's actually way more powerful. Uh, then we learn about assembly. That brings you even closer to hardware. Now you are telling the hardware, do this, followed by this, followed by this, followed by this, followed by this. That's why we call them instruction, right? The definition of instruction is basically I command someone to do something. That is what assembly is doing. Do it one at a time, one instruction that are simple. Hardware can definitely understand that instruction. You now speak the language super close to the hardware. Then we talk about data representation. Data representation basically tell you how you actually map the data that you see onto the hardware. How does it represent the numbers? How does it represent a floating point number? How does it represent character or letters? Right? Then we talk about cache and virtual memory. Everything here combined tells you like the basic of computer organization. So at the end of the day, you kind of like getting to know how computer works, right? So today I'm gonna talk about, so today it should be more relaxed, right? Feel free to ask me any questions related to these material. I just want to give you like, okay, what's the future if you look into this computer system or like things that are closer to the hardware, what does it open up? But anything after this slide is my own opinion. I also, because I'm not like, I don't know everything. So there'll be some point that I will just say that, okay, this is as much as I know. Uh, if you want to look it up even further, then you can check with me. I can tell you who to contact to learn more. But yeah, what's next, right? So right now below here is list of bullet points that you see are sample of topics that basically open up. after you take this class, right? Obviously, OS required for all 60, 61, and 62 students? Maybe. I think you need to. Oh, no, okay. Basically, OS is like telling you how you build Linux. How does it, like, what does it consist of? I will have slides on that explain a little bit more about like what is going on in computer systems. But this topic, so I think all you heard about the cloud, right? And I think all you now heard about IoT. You have to live in a cave if you never heard of the word IoT. Basically, the backbone of IoT. Don't look at what people in Thailand are treating this topic. They're all like, I would say 99% are still have a wrong understanding of what exactly is IoT. You don't look at it as a user. The backbone is actually computer system. How do you integrate all these small devices together has a lot to do with things like the operating system, distributed systems, communication, right? All those things. Then it opened up things like computer network. You can now take computer network class. You can look into computer security, well, with a little bit of caveat that you need to also know math, like numerical method, or things like number theory. You need to know those things as well to know computer security. So I would definitely check with Ajahn Kanat if you are interested in that math based direction. But from the system side, once you know how computer works, you know where are the vulnerability. Um, I think there was a pretty interesting discussion during the office hour on Friday where some of the students are asking about like, okay, what about hacking? Like, can you hack if you know C, if you know computer? And my answer is yes, it is one of the requirement. You need to know how computer works. Then there are things like compiler and compiler optimization that kind of stem from the fact that you have assembly, right? The assembly, the way you write the code, it change performance. Compiler is like this automatic tool that would give you good performance. So one branch of computer science is you then work on the compiler, you create a new compiler, right? If you look at GCC, for example, the compiler that compiles C code, right? You notice that there were version of GCC. It starts from like back in the 90s, right? And now you're at version, I think 10 plus, right? Uh, each iteration improves certain aspect of the language and certain aspect of the optimization. It make your program magically faster with new compiler. So it's another interesting branch of computer science that you can look into. The other two that I kind of would pair together as like things like database system, where you learn then with the knowledge of the code and knowledge of like how the memory is organized, how your data is organized, then you can talk about how do you actually build a database, how do you build a data warehouse, how do you make it fast? I think one of the main struggle of most company in Thailand, as far as I've seen so far in the past year, they always come whenever I go to like give or meet with a company on about like about their infrastructure, one of the main complaints is like they have a database, but whenever they want to get some data, it's so slow. And my answer is yes, because you don't know what's running behind it, right? So if the way you install it, yes, you install the database system, it works, but it's really slow. What is open section? What does it mean when you said open section? Is it certain? Does it mean certain thing? I'm curious. Oh, yeah, that's one of the. So I think that in probably involving like database system, also involved with like the computer that you install the software, and also how you design the software. Think about this way. Whenever you use a file pointer, right, the file pointer needs to point to the location of hard drive. Oh my God, that's just so bad. Yeah, so if every time you open it and it actually need to get all the whole like Sky websites and all the data, it's going to be slow. Okay, maybe that's also why Sky is so slow. And from my personal experience, like this is so slow. But yeah, if you know system, right, you will then exactly, that's a great comment. So the comment like, can we use the cache for database? I heard some call Redis, and it looks interesting. Yes, it's a really common technique. We call this in-memory database. Typically, a database system would put the database in a hard drive or in the solid state drive, right? And then you query. Query means that you basically go and grab the data. Now that your RAM is big enough, like you have hundreds of gigabytes of RAM on the server grade computer that holds the database. One of the one of the ideas that researchers propose and we use it all the time these days are, hey, we have big RAM, so let's bring in those files and cache it in the DRAM. And then with the fact that you cache the data into this RAM, right? You can then use the L1 and L2 cache as well. So yes, it's a really common technique. We would then cache data in from the database in hard drive into the memory. Whenever I said memory is slow, hard drive is even slower. That's why one of the main reasons in a lot of database systems in Thailand, they never think about this thing. When people design, they just want to install it so that it works. I never say that that's a working database. I would say that's a crappy database, but hey, don't tell people that I said that. It's an annoying problem that's been solved in the world, and they just don't know how to do it. So I hope that you will then graduate like, hey, you should be aware of the what people call backend, right, and how it works, so you can make this fast. Uh, And then there's also like topic of parallel programming. Parallel programming is basically you have a program. How can you make that even faster? Now you have multi-core processor or GPU. I'm going to talk about this topic a little bit more in detail. And also embedded system, which is a part of the IoT push these days, where you have these little devices. Let me. Yeah. So have you seen this thing on the video here? I Basically, I'm showing you the Jetson Nano board. Yeah, NVIDIA Jetson. What it is basically is integrated. You have a CPU in there, a really weak CPU, and you have a pretty weak GPU in there as well. You can use it to like do something simple like face recognition software. Uh, this particular board, I was thinking about like maybe I will set it up in a car, so that I can measure the things like accelerations. I will try to like stream the video and see can I get some data for the self-driving car projects that I'm trying to launch, right? So these things basically are becoming more and more powerful. Like it's really small. It's a relatively small and like light devices. You can put it everywhere in around you. It's actually cheap enough. I think this one is about like 5,000 baht, right? Compared to a full-blown computer, which is like uh 20,000. You can put it like more of these things, connect it to the network, and then have them do something useful, right? This is part of the distributed systems and embedded system and computer networks combined to have this functioning system that can run IoT workload. And then there's computer architecture, which I'm going to go into detail. But let me first begin from the computer system aspect. I'm going to go through the topic that I know, and I'm going to leave it up to like you to, I guess, ask me. That's okay too. I'll forward to people who know this topic. one of the things I'm trying to do in the past years, I'm trying to like basically gather a group of people that I believe that they are good enough for certain topics, so I can have a good like discussion with. So if you're curious, I can point to the right people in the country and who I think can guide you on certain topics. But for computer systems, basically, if you're interested, definitely take the OS class. In that class, you learn how to build a functional operating systems, right? It would involve things like kernel hacking. I think in the class, you're not going to start with a kernel code that's too complex, but then you build little functionality at a time that are key to the functioning operating systems. What are those? One of them is now that you have a lot of programs running, again, I use this example all the time. You have 20 Chrome tabs, right? Each of those tabs is its own thread of the small program. How would you map all those 20 tabs onto your multi-core? You have only 4 or 8 cores, right? It means that you have to stop 12 of them. And you have to switch all the time, switch between those 20 and who get to run, who get to use the CPU. The OS has to make that decision. It has to look into all these ongoing tasks and see, okay, you go, now it's your turn, now it's your turn to run, now it's your turn to run, and make sure that none of this application is too slow. Why is that the case? If the program you're running becomes too slow, the user notices it. This is all about hiding it from the user, hiding the fact that you're not running everything at the same time. The OS on the mobile phone also has to manage this as well, right? For example, I just had a paper last month about like when you have this foreground application, the application that's on your screen in the mobile phone, right? You need to prioritize that so that the user doesn't feel like it's slow. And then you can kind of like ignore the background application because if you think about it, some apps you open it and you forgot that you open it, you switch to another app and you left it there for like 30 days. How many people do that? Let me check my phone right now, right? For example, on my phone, I have a I have an app from like United Airlines that I open in January and I haven't closed it yet. Like I can show it to you here. It's a United Airline app that I haven't. Yeah, it's these things that show you. It's actually it's kind of like running in low power, low requirement, low resource mode in the background, right? If you learn the OS, it actually do some tricks with it. It actually would close it up, but hiding it from you. Um, so yeah, so on the mobile phone, it's still running that. That's why you can actually switch it back, right? But it would have different operating mode. The one that's in the foreground, the one that's like in the background, the one that's like you haven't opened this in 30 days. Kick the data out of DRAM. I'm sure if you look at that United app, for example, the data from that app is not in the DRAM anymore, right? So the OS, the operating system designed those policies. How to manage data mapping. Now you learn virtual memory. You know that, hey, you need to have this page table structure, right? The way you organize a page table structure impact performance. Like how to map the data to different memory or storage devices, how to handle page fault. So if you use virtual machine before, you probably realize it's super slow, it's annoying, right? How many of you think that? So if you missing a TLB in the VM in VirtualBox, we were talking about for DRAM access for 4-level page table, right? You remember from the virtual memory slide? It's basically 4 trips to DRAM to get your data, to actually get your physical address inside the virtual machine. That becomes 24. Why is it 24? Because inside the virtual machine, you have this own page walk. But every time you go to DRAM in the virtual machine, that's a virtual address because VirtualBox is a program. That program still maintains virtual address. So locally on your machine, that is a virtual address. So every time you go one level, you need to do the walk on the virtual machine, followed by the walk on the physical machine. And that's why it's 24 accesses. It's bad. Uh, this is also another reason why you don't want to always throw everything into the cloud. Because a lot of the time, the cloud environment is using something like a virtual box. It's better. It's better, but it's not perfect. It is going to be still slower than running things locally. Uh, Handling page fault, right? When you have limited DRAM, which page get evicted, which page is brought into from the hard disk. The other part is about using shared library. So if you use Python before, how many use Python and use to like plot the figure, or use Python to do like use this like shared library to like kind of like almost like this include thing in C? If you use it, those are shared programs, right? The OS has to figure out the way to let everyone use it. And someone, if they modify it, if they modify the content of the data or content of the program, everyone else has to see that. How do you synchronize? How do you manage all the data that gets moved around and modified all the time? This is another big topic in computer system. What's more, if you want to build cloud infrastructure, I'm not talking about using the cloud. Now I'm talking about building the cloud, right? It's possible. That's what Amazon is doing. That's what Microsoft is doing. I don't see why we can't do that. All the knowledge is already out there. But basically, you have to then learn how to manage data communication, how to synchronize the data, how to actually build a functioning system. So if you want a functioning IoT infrastructure, you need to know computer systems. If you talk to your friends and they claim that they know IoT, but they never take anything related to computer system before, they're not really building IoT system, they're just using it, right? Uh, and also this part, there's a part I don't like about the move in Thailand about like, hey, we need to have IoT system. I don't think we have enough expert in computer system and like architecture to build this system well enough. We do have experts, but the people who are actively working on this area who claim they know IoT are not. Otherwise, I would know them. Uh, how to build a high performance computing cluster. Let's say you want to run a program that would analyze the RNA sequence of the COVID virus, right? It's a totally legit workload. You want to analyze the RNA sequence of COVID. So you then can figure out who would be more susceptible to this virus and who is like maybe they would get infected, but they're not going to see like a lot of symptoms. So that you can filter out groups that are really, really like weak against the virus, right? These things have biology aspect to it, and it actually requires so much computation power. So the computer system designer would come in and say, okay, this is how you build the computer, a large cluster of computer to handle this case, right? And we do actually one of the good push I see in the country so far is, do you know that NECTEC actually is building, they finished it now. Basically now they have a center that you can run high performance workload in it. It's called Thai supercomputer. If you haven't heard about it, look it up. So people over there are just doing really cool thing, and now we have a really large scale computer cluster that you can use. if you want to do a good research on certain aspect of things like bioinformatics, things like weather prediction, anything that related to large scale ML on those like non natural language processing. How to ensure that computer eventually see the same value, right? What does it mean? So I assume that many of you here use things like Instagram or Facebook, right? What would happen when you upload a new thing? Like let's say you upload a new picture on Instagram. You want to make sure that eventually everyone see my updates, right? If you look at your friend's profile, you should see the most up-to-date version of it. Have you ever think about what has to happen inside the computer in the server to make sure that no matter what you connect to in terms of server, right? If you use Instagram in Thailand, you're likely to be access to the server in Thailand or in Singapore, like somewhere close by, right? But let's say your friend is in the US, they upload their picture, right? That picture will be first uploaded to the server in the US. Eventually, the server in Singapore or in Thailand need to have that recent version of the profile, right? You need to think about what's going on inside to actually make sure everything is synchronized and making sure it's in the same order. In fact, if you heard of this name, I'm not sure if you heard of it or not, but there's a guy called Leslie Lampert who worked in these area. He actually got a Turing Award, which is kind of like a Nobel Prize for computer scientists, right? Because he worked on these area and he kind of like revolutionized the whole thing and make sure that company like Google, Facebook can have a really fast way to synchronize the data. So it's pretty big, right? It's a pretty big problem that you might not be aware of right now. But if you know computer system, no, see, everything starts from knowing how to write C code, knowing how cache works, knowing how virtual memory works, knowing how data is represented. It evolved from there to the point that you can actually build something impact and meaning with like that are meaningful, right? Generally, this is the area where a lot of people would call it back end, quote unquote. The word back end is something I absolutely hate because it's too vague. I can't tell you what do you mean by back end. Do you mean the libraries? Do you mean the how you manage the server? Do you mean how you manage the data inside the computer? Do you mean the database system? Do you mean the storage, the file system? So hopefully in the future, if you heard about backend, maybe you ask like, what do you mean by backend? Which part of the system that you're talking about, right? But yeah, generally this is an area where a lot of people would call it backend. Then let's talk about compiler, right? So one of the things that you learn in this class is assembly, right? I hope you still have the distant memory that we talk about how jump instruction works. Uh, how would you build the jump table to handle switch case? If you don't have any of those recollection, I definitely recommend you remember it before the exam. But yeah, so we talk about how to translate your code into assembly. Compiler also look into how you can optimize your code to even faster assembly. Also things like how to represent the program in a way that's easier to optimize the code. What's the best method to map your program to different hardware, right? For example, even with this, the NVIDIA Jetson, right? It has a CPU and it has the GPU, the graphic card. So compiler is also responsible for like, should I run this on the CPU or should I run this on the GPU, and how to make sure I can have the code that works for both of them, right? Because they talk different language. Uh, how to deal with loops. This is another big question in compiler. Why is that the case? How many of you write a program with big loops? How many of you write program that has like for I equals 0 or something, and that's like the only thing you do in the function, looping in this big loop? It is really common, right? So if you can optimize the number of times you loop around, you save a lot of, basically you make the program faster. How to deal with data access. I think this is probably in line with what we teach in this class. Basically, go to the memory, takes so much time, use the register. Another side topic is on programming languages, which MUIC has the OPL class, right? So that class, we would kind of basically talk about what is the element of the program. Why do you have to have this painful thing in C that you have to deal with? What is the assumption? What does it mean to have a scope and like this function calls, the way it works? Uh, and then how would you design a language? And it's also like kind of like involved with things like compiler and code optimization. Because if you put it back into like how does each of these topics are related, at the end of the day, we want performance, we want correctness, right? You want to make sure the code is correct, that's the first order of thing. Then you want to make sure it's fast. Most of these topics are trying to get you both of them. And then there's embedded system, where you would look at different low power devices and you would then hack. Basically, generally in embedded systems is what you do. You plug a sensor into these devices, read something, process the data, and send it out. That's probably the high level idea of what they do, right? So this means that because the device is so small, it's going to involve a lot of kernel hacking. Basically, you're gonna build something like an OS, like operating system or Linux, but limited version of that. It only supports certain things that you want them to do, but not more. The more you support, the more it burns power and the more wasteful it is. So you have to think about, okay, this is the only thing I want device to do. So I just need the support for that and not more. It also involves a lot of assembly code, basically writing code in assembly. So if you hate assembly, think about it when you go into embedded system, because you want to write things by hand to make sure you improve the code size, make it small, right? And improve code efficiency. This is one main key thing that people in Thailand, as far as I've seen, they forgot about it. So your IoT system is really inefficient, and that's bad, right? So you want to improve it. The other one is it also involves the task scheduler. This is the same concept as computer system. So you have one device, you have many things you need to do. How do you manage the deadline? One example is if I have a self-driving car, I want to make sure I can analyze if the object I'm seeing is a human or not, the one in front of me, right? Definitely before the time I can hit the brake. Otherwise, it's either you die or that person die or both, right? It involves a lot of dangerous situation that you have to make sure you never miss the deadline. So this is a big topic in embedded system. Storage system are basically how to manage the hard drive storage devices to make sure that they run fine, right? How many of you have a drive that get broken and you lost all your data? Does it ever happen to anyone here before? You lost the data because hard drive is basically broken. Yes, no. The lack of anyone saying yes, I assume that that never happened to you before. It does happen to me before. It's painful. People who work in storage system would look into how to improve that situation, right? How to make how to make the hard drive fast, even though the actual device is not that fast. Uh, how do you improve reliability? Right? What if your disk crash? How many of you here heard about the word RAID? RAID. Have you heard of that word? Oh, uh, okay, yeah. So let me let me address the question that are a little bit off topic, but I don't know because so let me answer the question of whether this course will be open again next term or not. I think it partially would depend on if MUIC have someone to, because I'm a part-time lecturer, right? So whenever they have the internal meeting of what course we offer, it depends on them to make the decision. I don't really involve. I'm basically will be told like, okay, I'm gonna teach this class, I'm gonna teach that class. Personally, if I know it ahead of time, would be great so that I can find like if anyone want to be a TA, because grading 30 or more people without a TA is like fun, right? You guys are so creative with your answer. Uh, but yeah, anyway, so let's go back to RAID, right? It is basically multiple disks being plugged in together. One benefit of RAID is different on the depending on the RAID level. You can actually have one broken hard drive. You can take it out, replace it with a new hard drive. Everything would be magically working. You don't lose the data. So that's why RAID is really powerful. uh, the person who invented it was a CMU professor. I think he's in Toronto now. He was in the sister lab where I worked when I was a CMU PhD student, and that group also worked on a lot of storage system. One of the things that they're working on are like in-memory database, like Redis, right? The go back to the question you have earlier. That's why I pair up storage system with database system. Basically, they would work on how to make a good database, how to make it fast, how to make it reliable. Like you don't want to lose the data. This is like one of the really, really big thing over there in storage system. Uh, the paper I just published with the group from Hong Kong was all about like, okay, how do I manage the storage in the mobile phone where you have 5G, right? And then you also have the internal memory. Then you have the fact that you have background and foreground applications. So how would you manage the data between the foreground and the background application in a way that improve user experience? So these are key issues in storage systems. Then let's talk about parallel programming because you guys definitely have one expert over there, which is Ajahn Kanat, right? But basically the idea is like now that you have multiple cores or you have a GPU, right? I think some, huh? Oh, okay. So system skill is a prerequisite for data structure, is it? No. Oh, okay, okay, okay. I see, I see. All right. I was panicking because I was asking you to build the queue in the exam. Like, if it's a prerequisite for data structure, that's a bad thing because it's a different order. Now, okay, it made me feel a lot worse compared to the worst, like not good feeling. Oh, parallel programming. Uh, no, I think you need to know data structure before parallel programming, I think. Basically, it is all about how to use all this processor. Uh, yeah, I agree. Data structure has to be like a prereq for almost anything. I think SysQ can be done without data structure, but then I need to kind of like be aware of it so that I change the midterm and I change the some of the assignment to be less involved in terms of data structure and more focused on C. But some super basic data structure would be good to have. All right, so let's go back to parallel programming now that we are a little bit off topic here. Basically the idea is like now you buy a computer with multiple CPU. How do you take advantage of that? How many of you heard about mining Bitcoin using a GPU? Yeah, so it was a pretty big thing back in like 2 or 3 years ago when it's still beneficial. Like you can still make profit by buying one GPU and run it. Now, if you do it right now, you probably pay more to pay for the basically the power consumption than the money you gain from Bitcoin because of two things. It's actually harder to mine now because the way Bitcoin is designed. The more people found this coin, the less chance that you have to find the next one, right? And the other thing is Bitcoin, the price nowadays is actually dropping quite a bit, right? It is super inflated in the beginning, and now it's like, okay, it's kind of level off. But there was a period where people used GPU to mine Bitcoin because Bitcoin workload is super parallel. You would mine like 1,000 different hash at the same time, and hopefully you get the coin. Um, you also, I think, right now heard about things like machine learning, right? Deep learning. How many of you heard about deep learning? So deep learning involves basically the key concept behind deep learning. It goes back to how fast you can do metrics multiply. Deep learning is all about making metrics multiply really fast. The GPU is good at multiplying metrics, so they use the GPU for that. Tensor Core, a part of the hardware design inside the GPU, is actually a concept back in the day, right, that would improve how you do matrix multiply and multiply, accumulate. Basically, multiply, then multiply, then add. So it's all about like parallel programming. Basically, in general, you think about how to change the algorithm that you learn, painfully learn from the algorithm class, right? And think about, okay, what if you can do two things at the same time, or like five things at the same time, or n things at the same time? Can I parallelize my algorithm, right? Uh, at the same time, you need to be aware of the hardware constraint and deal with things like data synchronization. So another big concept is like how to reduce sequential bottlenecks. So if you, I think there's one of you here who took like Ajahn Kanat's like advanced algorithm from last semester. But then if you did that, you would then realize that one of the problems that people who work on parallel programming have to solve is like how to get rid of these sequential bottlenecks. Uh, I'm not going to talk about this in detail. It's a little bit more advanced. I would cover this in an architecture class. But basically, if you can solve this, it make your program faster. Uh, oops. And then these are example of parallel programming language or framework, things like Rust, Silk, OpenMP. So I see some names here who take this class and you used Rust before. Uh, can you share your experience using Rust? You can send me a private message too. I just want to get out. Okay. All right. So the answer was interesting. Basically, you hate Rust. Trauma. Okay. 100 scale. All right. Okay. My God. Okay. Basically, these are parallel programming based languages that are designed to be really fast. But the caveat is it also is annoying to program. If you think sex fault give you trauma, this would give you like the next level trauma, which I think you all who answer me would agree with me. Is it? Compared to sex fault, is which one is worse? Okay, totally agree on sex fault is better. All right, so these things, the reason why they are annoying is like you need to think about multiple things at the same time, and human brain is not designed for that unless you have Ajahn Kanat's brain. I don't know how it works. It's magical, and he's like one of the expert in like parallel algorithm in the world, right? he actually got like a lot of respect in the research community because he is the expert in this area. But if you are interested in this, feel free to either talk to me or Ajahn Kanat. Like I would do this from the hardware side. Right? I would try to solve the hardware constraint. I would build the hardware, assuming that the program that Ajahn Kanat write is like the God. I can't change it. And then he'll be like designing the program, assuming the hardware is the God where he cannot change the hardware. So yeah, this is one of the thing that you guys have like one of the best resource I would say in the country on this particular topic. Uh, what else? Okay, so now I'm gonna talk about my own area. This is my comfort zone, architecture. So what is an architecture? What is architecting, right? So do you know what it is? What, you never seen this? All right, hint, it's in Paris. Yeah, it's a museum with Mona Lisa in it. It's a Louvre, right? So this is one of the benefit of being a PhD student. When you present your work, you need to go to a conference. It just happened that one of my conference happened in Paris. So I fly there, give a talk, and then I told my advisor I'm gonna take 1 or 2 days off, and I basically roam around in Paris. Um, you see how they built this thing, and then actual museum is actually underground from this picture, right? It's a good piece of architecture, right? It's actually built to attract people into like what the heck is this pyramid thing? Uh, and then inside that, right, you see how they like break it down to different sections based on different, I guess, region of like art and like the piece of work that they house, right? Uh, this is especially part of the real world architect. You build something, right? So is this an impressive work of architecting? I would say yes, right? It is a pretty complex thing to build this museum. And it's designed by one of the master like architecture. What about this? It's a waterfall, right? Everyone can see it's a waterfall. This is actually close by Pittsburgh in CMU. CMU is in Pittsburgh. This waterfall is about 1.5 hours from CMU. I actually took picture on this trip that I go with Ajahn Kanat back when we are both at CMU actually. And he actually spot this angle and like, hey, this is a good spot to take picture. We both like photography, and we basically hang out quite a bit to take photograph around Pittsburgh. But there was a guy with a lot of money back in the day, I think it's 100 or 200 years ago, that say, hey, I have money. I want to build a house on the waterfall. Is that a demanding question? Like building a house on a waterfall. So it's actually a part of the job of architect, right? The architect has to think about, okay, with this crazy goal, if I want to take his money, I mean, at the end of the day, people still charge for that, right? If I want to take his money, how can I build a house on a waterfall? This is one of the UNESCO World Heritage Site, uh, right around the corner of the waterfall I showed earlier. This building is close to it. It's called Falling Water, and it's designed by Frank Lloyd Wright, one of the master architects in the U.S. Right, and you see that it's actually a house built on the waterfall, right? So this is what architects do. We take in the user's goal and we build something, right? We build something to satisfy the goal, to make it functional, to make it good in a sense that you need to be able to live in there. You need to be able to enjoy living in there, right? It need to meet all the functional goals. And at the end of the day, it has to be cost effective, right? You need to be able to find a way to build it. Sometimes goals are crazy, right? Uh, so this is what we do. We design a computer. In computer architecture, we design the whole computer, and basically involve like how do you get the put everything together based on the requirements. So what does it mean? So you need to fundamentally understand the circuits for the architecture class I'm teaching you. You don't have to know that. I'll just give you the high level overview enough for you to make some trade-off, right? Whenever I say like bits are ones and zero, that's the amount of information you need to know. You need to be able to picture it to like physics, but you don't have to always understand the physics. You need to fundamentally understand the software. This is the important part. You need to know how the software works, what's their demand, right? Even want to run Bitcoin, what is Bitcoin? What do they do? What is the common algorithm behind Bitcoin? If I want to run a machine learning application, you need to know that it's actually matrix multiply, right? So if you know that, you can build the hardware to do matrix multiply really fast. uh, you want to make sure you satisfy the user's demand, right? Someone basically paying you to do something, so you need to satisfy that. And why is this important? The first use case is for performance. At the end of the day, if you are like a typical programmer, I'm sure you can produce correct result, right? If you spend time like maybe a month debugging, you get a functioning program. So the first bullet point is relatively common, right? And if you graduate a CS degree, you should be able to satisfy that. So the second bullet point, basically, you want to be able to write faster code, right? But to get there, you need to know how to optimize the code so that they're fast, right? The example here is things like high performance machine learning or self-driving car. You need to make sure they're efficient, they're fast. Knowing architecture, knowing how computer works will help you writing better program. Uh, you want to also make sure you have service guarantee, right? You are paid to deliver certain things. For example, how many of you would refresh a Chrome browser if you don't see the actual website for how many seconds? Can someone tell me how long you're willing to wait for the website to actually show the content? 1 minute. Okay, you are really, really patient. 20 seconds, that's more, that's more than a normal range. All right, maybe 10 seconds. Okay, so yeah, so different one of you would have different level of patience, right? And at the end of the day, you want to make sure that's as fast as possible. You agree, right? At the end of the day, you want to make sure the website is generated for you as soon as possible. And it should have certain guarantee that after say 1 minute, uh, you need to somehow do something, right? Knowing how the hardware works make it a lot easier for you to provide the guarantee. You can tell the user that, hey, I can design a program and I can ensure you that most of the time within 5 seconds you see the web page. But then within say 1 minute, it's guaranteed that the web page will be generated, right? And then you can build your program based on the hardware information. This is really, really important in embedded systems, things like self-driving car, right? You need to provide a guarantee that you need to be able to detect an object before you hit it. Otherwise, you crash into an object. So this is another important aspect of knowing the hardware would help in these scenarios. Uh, Another case is for energy. You want, like for example, your mobile phone. This is an obvious example. You want the battery to last for 1 day, right? So you not have to recharge my phone once in a while, every time during the day. Writing energy efficient mobile apps is actually hard. How many of you download an app and somehow when you use it, it drains the battery like a madman? It really common in games actually. So I'm sure for those of you who play mobile phone games, you have to like always recharge your phone during the day. But if you don't play the games, then you realize your phone actually lasts one day without having to recharge. So knowing how to minimize the energy consumption can be a good thing, right? For cost, obviously you want to be as cheap as possible. Why should I replace my desktop all the time if I can buy, if I can design a better CPU? This is like a core of what we do. We buy better chips. I mean, not we buy. We design better chips. We design larger memory. That's actually the reason behind the fact that you get to use like 16 gigabyte of memory versus 8 gigabyte is because of the advance in computer architecture. Uh, so the key takeaway is even though you're not gonna plan to work in hardware or like build chips, right? Knowing this thing would make you write a better code. More reasons, if you look at how this advance in technology, this new technology is all about advance in hardware. Why is that the case? Well, modern day machine learning is actually a hardware that you can run it on a GPU. GPU is essentially a combination of two old concepts in architecture. The TensorFlow that run on Tensor Core is another variation of this old architecture concept called historic array. I think it's proposed in 1960 by one of the researcher who say, okay, you can do matrix multiply using these design. It will be fast, it will be energy efficient, so you can use them basically now to accelerate machine learning. Uh, it has a lot of use in IoT. How to design the hardware to be power efficient, how to design the hardware to meet the goals or the user goal, and how to create all the devices that can operate in a different way. How can you make sure that what if one of the device go offline? How can you make sure you still have a functioning IoT system? And I think by this point, I think I realized that a lot of you play computer games, right? Including myself, I do play games too. So new piece of hardware like a graphic card enable like cool graphic videos and games. If you look at Pixar movie from 10 years ago, like Toy Story, the first one, the first Toy Story versus what's the what's the latest like Pixar movie? I forgot. Like the one that came out like last year or the 2 years ago. You will notice how different they look. Is actually much, much better. Look at the water reflection. Look at how they model this like the hair, the skin. Skin is actually always hard to model. The reason behind that, if you look at your skin, the light actually come in, it go inside your skin a little bit and bounce around before it come out, right? So to model this, to model the skin properly, there's a lot of computational, basically a lot of computation involved. So you need a really, really powerful GPU. But now it's getting better and better, right? So these are additional reasons that you might want to like say, hey, I'm interested in architecture. Uh, any questions about the topic we covered so far? Because I'm gonna go back to the in-class exercise and make sure I answer all the questions from in-class exercise 11 or anything we talk about today. So today is it won't go into your exam. Trust me, it is unrelated. I just want to bring it out because you are now like this is like the first class you're taking that are closer to computer systems. So I want to give you a brief overview of, okay, what else? What's next, right? What would be interesting classes you can take? So let me answer the question about whether you have to know or you have to code well to be a computer architect. I'm not a good coder, I can tell you that. Like my code is ugly. Uh, you don't have to be great at coding. I would say if you want to look into computer system or hack kernels, then you might want to be like you have to be a little bit more skillful with coding. People in computer architecture area, we would do more of a design, and then the code involved in this area are how would you model your design, right? So hopefully that answered the question. Do you have to be like, super good at that? If you're good at it, it helps, but you don't have to be like super, super good at it. But you need to know how computer works. In class exercise 8. All right. So I can go back to in class exercise 8, but let me pull it up. I actually forgot what it is. Sorry, it was a long time ago. So let's talk in class exercise. Okay, about assembly. Is it the worksheet? All right. So if anyone has any question about in class exercise 11, I will context switch. The word context switch means that I'm gonna switch to in class exercise 11 questions. But in the meantime, I'm gonna show the class exercise 8. What is your question so I can explain? All right. So you don't get number 5. Let's see. So if you finish with in class exercise 11, this is it for the class, right? For today's class. Next class on Wednesday, it's all review and Q&A. If you come in with no question, it'll be a really quick lecture, but I would love for you to come and ask questions. Problem 5, what is that? Okay, so this program test is a for loop. So what is the part that you don't get? Can I at least see where you get stuck with?ขอบคุณมากอ่า can you tell me like what part of number 5 where the all right, so let me break it down. Let me share the screen, right? So that it's a little bit easier here. Oh, okay. So then let me share the screen on that worksheet so I can go through step by step. Give me 1 second. I'm gonna open it on my laptop so I can share it. No, wrong link. And for those who haven't started in class 11, I definitely recommend you to start it. That's from the last semester final. And there's a chance you get something similar. And it might look overwhelming. That's my warning behind the in-class exercise. It might look overwhelming, but it's actually it's not hard if you know what you're doing. Download this so I can write on it. so let me switch the screen. Wait, I guess I need to stop sharing. All right, can you see my PDF? Okay. All right. So when you see a question like this, my recommendation, where's my pen? All right, here. So my recommendation is to first look at the structure here so that you know what the code is doing from the C side, right? From the C side of thing, you know that okay, the first thing that you need to do or you need to tell is there'll be some initialization into results, right here. And then there's a loop. What does the loop do? It first initialize something, condition check, and then when at the end you do something else. Inside the loop is only one thing, right? So if you look at this part, what can you tell me? Let's break it down. What would make you exit the loop? If you're at L7, if you're at L7, you're done with the loop, right? Which means that if these become true, jump greater or equal L7, then you are out of the loop, right? So what do you do with the jump greater or equal? What are you comparing with? This, right? ECX and EDX. So what is ECX? Yep. So what is ECX and what is EDX? So let me go back to the lecture that talks about this so I can tell you the lecture number and where's it? So if you go to lecture 11, slides number 55, lecture 11 slides number 655, you will know that ECX and EDX are part of the input, but you then also know that, hey, ECX and EDX are the third and the fourth input, right? Which is not here. So the next thing you need to check out is ECX is being moved here, right? Someone is putting the value of ECX in here. Oh, yeah, sure. I can talk again. Basically, the compare ECX and EDX, right? Compare it's basically compare ECX and EDX. What's in ECX? What's in EDX? ECX is you can look at this. It's actually whatever this address of the base pointer plus 12. And then what's in EDX is basically whatever is in the base pointer plus 8. Right? So basically these comparison, both of these comparison would go these two things would go in here. Is that condition checked to exit the loop? Another thing you realize, which is like, let's get it out ahead of time now, is you have this. Move one into EAX, right? Move one into EAX. Which one is the MPL? It's compare. Compare. The combination of CMPL and jump is the comparison. Sorry. Is the if-else statement or the condition check in the loop. Basically tell whether you go do this or go do the other thing. So do you then use CMPL and jump? Because CMPL would set the correct condition and jump would check the condition and go based on the condition. But the first thing, the other thing you see is this move, right? Move out one EAX. What is EAX? EAX is a return value. What are you returning? Results, right? So you know from this line, you're moving one into EAX. Basically, you're initializing results to one in the beginning. So are you with me so far? Basically, that line, you know that result is one. Oh, the result part. Because you look at the C code, you know that you're doing something with results and you're returning results, right? You're doing something with results and you're returning it. And if you look back at the assembly, the only part that initializes something to the return value, which is EAX, is that line, this line. What does that line do? Oh, EAX by convention, basically EAX is the return value. So when you finish the function, once you hit return, EAX becomes its return value, and you know that, okay, you return results of this EAX. So then you know that this line right here, right, it moved one into EAX. Okay, so it means that I'm initializing results to one, right? Okay, then what is ECX and EDX? Hint is it has to do with X and Y. Basically, these are the other two that you need to check. So which one is X and which one is Y? Someone help me. Someone help your friends. Which one is X and which one is Y? And also why is that the case? Yeah, so the common wait. So yeah, so the answer is ECX is Y and EDX is X. Why is that? Why is that true? It has to do with these two lines, right? It has to do with these two lines and also the assumption with the, again, the IA32, like a 32-bit of assembly assumption that it tells when you call a function, the input to the function would be stored where? It would be stored because it get pushed into the stack. It get pushed into the stack. The earlier input, right? The earlier input If you go to slide, I'm trying to find the corresponding slide on the lecture so that you can come back. Let me open up the lecture quickly. All right, it should be on assembly part 3. And slide number 24. Slide number 24 of assembly part 3. Basically, if you look at the stack, that grows up, right? Your base pointer is right here. The earlier argument is the first one, from here. So the +8 is the earlier argument. The one that's +8 is x. The one that's +12 is y, right? The one that's +8 is 12. The one is plus 12 is y. So this is +12, so this y, and this +8, that is x. So EDX is x, and then ECX is y. What does it compare to? It compares ECX to EDX, right? And if it's greater than, if ECX is greater or equal to EDX, you exit the loop. So you know that, okay, this is what I need to do. If ECX, which is y, right? If y is less than x, you stay in the loop. Otherwise, you exit the loop. You know that you then add, right? You then add to EDX. What is EDX? Oh, that's a multiply. IMUL is a multiply. Yeah, so this is y plus equal to. What is the initial condition? Okay, let's do the multiply first. Multiply is actually easy. So you multiply these two numbers. EX is result. EDX is what? Okay. So the y plus equal to is coming from here. So basically you add to the condition check. You add to the condition check so that basically that translates to, okay, I'm gonna increase this by 2. EDX is x. Did I write wrong? Yeah, EDX is x. Yep. Oh yeah. Sorry. Let me erase it. This part, right? Okay. My bad. My bad. I got confused with EDX and ECX. Sorry, you were correct. Yeah. EDX is x. So that should be x plus equal to. Yep. Here. Yes, that's correct. So what's the last line in here? Yep, results multiplied by x. Sorry, I'm also like, yes, that was another question that I want to ask. Why is it? Why is jump greater? So the question is like, wouldn't that be y is less than or equal to x because of the great jump greater or equal to? That jump greater or equal is going to exit the loop. So it's actually the inverse of that, right? So the equal part, once it's equal, you exit the loop. You mean this loop right here? Okay, so one at a time. Uh, that jump. So let's just go back to the jump. If y that's the next, yeah, that's the part of the loop. This jump is a part of the loop, right? The questions about why is I equal x, I equal x because basically this is what you multiply. You multiply edx to eax, right? You multiply edx to eax. What is it, edx? That's x, right? Edx is x. So initially, the first time you go into this loop, basically that means you do read. Oh, yeah, actually, I did something wrong here. This is not x plus equal to. This is I equal plus equal to. The actual thing that moving here is I. And this is result multiplied by I. The value x stay the same. It's not used anymore, basically. Okay, awesome. Any questions about the in class 11? Let me show it up. So for those of you who did not attend the lecture from Friday, let me show it to you. This is a question about virtual memory. The first part is not that intimidating. We are basically asking you what is the number of bits required for the page offset. You would then do log of 4 megabyte, right? That becomes 22. You then, based on this answer, you do the other three part. This is the part that you might be intimidated by because I basically do a memory dump. I give you the value of these addresses. And then if I have a virtual address like this, what's my physical address? Then with this question, if I given this virtual address, what's my physical address? So if you have questions about this in-class exercise, make sure you ask it sometime, either email, office hour on Wednesday. Definitely recommend you to take a look at it and try to solve it if you haven't done so yet. I now realize that I forgot to post a video from Friday. If you're stuck, you can also watch the video on Friday because we went through this in detail on Friday as well. And I hope that's more clear to all of you. So yeah, I'm gonna post a video as soon as possible. That's it for the class today. Any other questions?